Number 15 says, consider the equation sine 2x over 1 minus cos 2x equals cotan x. So it says determine on all non-permissible values for x. So the non-permissible values are going to occur where the denominator is equal to 0. Okay, so I'm going to look at my denominator here. And so I have a 1 minus cos 2x is equal to 0. So 1 minus cos 2x equals 0. I also have a denominator here that has a cosine in the denominator. So from that, I also have cosine x is not equal to 0. Okay, sorry, that's a sine. That's a sine. The cotan has a sine in the denominator, so it's going to be sine x not equal to 0. Okay, so then working out, solving for x, I'm going to end up with 1 is equal to cos 2x. Cosine is equal to 1 only at only at 0. So we know that 2x is equal to 0. X is equal to 0, and that's going to occur. This is going to be repetitions. So maybe I should write this down. Theta 1, and then 2x theta 2 is going to be equal to 2 pi. So x is going to be equal to pi. So that means that I'm going to have repetitions every pi radians. We can think of it as our primary solution is at 0, and our period is 2 pi. Sorry, 2 pi divided by 2, which is pi, so we can look at it that way as well. Or we can do it, analyze it for the full circle for 0 and 2 pi, and solve them independently and say that this occurs. These two solutions occur every 2 pi. In either case, when I combine these together, x cannot equal pi. Every increment of pi, it doesn't work. So n is an element of integers. So 0, pi, 2 pi, 3 pi, and the negatives as well. Solving for sine x equals 0, well, sine x equals to 0 in these two parts here, here and here. So x is equal to 0 and pi. So these are going to be the same repetitions as we had in the previous one. So we can combine this, and we're just going to stick with that one there. Okay, and maybe I should be clear about this one. This one, these are repetitions, so it's going to be 2 pi, 3 pi, dot, 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 dot. Okay, so those are our non-permissible values. It says, secondly, prove the equation is an identity for all permissible values of x. So I'm going to rewrite this expression. And the problem with this expression is that we have a 2x, so we have sine 2x, 1 minus cos 2x on one side, and the other side we have just an x. So to make these the same, I need to convert the 2x into a single angle. So the sine 2x only has one option. It has sine x, cos x. I'm going to convert the cotan into cosine x over sine x. Okay, so the cos 2x, we're going to use, we need to end up with an identity that gets rid of the 1. So to do that, we're going to use 1 minus 2 sine squared x. Now, there are 3 options here, but we need to get rid of that plus 1 by subtracting the identity. So that's why I chose the 1 minus 2 sine squared x, because that one will cancel the ones out. And then this will allow me to then simplify this identity. So I end up with 2 sine x cosine x over the ones cancel out. I have a doubled negative, so it's going to be positive 2 sine squared x. We should be able to see that the 2 and sine x cancel out, and so we're just going to be left with sine x over cos x on the left hand, cos x over sine x on the left hand side, and that's going to match our right hand side. I've now proven this identity.